It's my honor to introduce John Satterfield here today. John's invested more than 30 years into this business that we all love, and he's been able to develop a very typical presentation that people come here to see. In those 30 years, he's been able to refine his skills and become an expert in many different facets of performance engine design and concept and modification and, of course, testing and engineering overall. His presentation today is going to focus on looking over an entire project, plotting and planning that project everywhere from starting in your head, as he said, scribbling on a napkin, turning those dreams into reality, and investigating and researching each portion of the engine to make sure you come out with the absolute most efficient power plant you possibly can when you're finished. So without any further ado, it's my honor to introduce John Satterfield.
Thank you, Scott. Can you hear me? Oh, yes, I can hear me too. Excuse me. One of the things that it's like my life lives through my work, I strive for perfection. The hardest thing to do is to do your best. This conference, I remember I've been to all 13 conferences. Who I am and what I've come to be in life is a large base on my attendance to this conference. So I never withhold anything. I enjoy the success that this conference has brought me, the friendships, and family that this conference has brought me. So that anything that I have that I can bring to this conference, I always do. And that is the scope of my presentation. Giving back to those that give me. It's not how many people you knock down to get to where your goals are. It's how many people you pick up along the way. An idea has to start somewhere. Second place is the first loser. Be competitive. My best ideas start during a workout or hiking or at dinner. And if you can see it, it's a napkin and it's in your handout as well. Or just drawing a little something, because I don't go to bed, I don't go hiking. Other than being in a swimming pool, I have paper and pencil with me. I also like to give the answers first, because that allows you to know where I'm going through the process of these thoughts. It'd be very hard to remember every word. So the finished project is what you see in front of you first. It's my Ford project. About 8 years ago, I started talking about this project here at the conferences. This project was actually finished 7 years ago. So what everything you see here now was actually done 7 years ago, and it's still advanced to this day. Project engine, preparation and porting. Okay. Design the engine for horsepower. And I'm going to qualify my statements here today because each application does take something different. These are for single four-barrel, at sea level, maximum performance engines. I will try to qualify my statements when I can, and remember to do so. The place to start. Well, one of the things that I've learned from working with the Cup teams and myself is we can have a pretty good indication of how much air we need by the estimation of power or measured power. So I made up a little formula. Some of these are just John things, but I thought, this is a time to share them with everybody. We have horsepower, an 8-cylinder in this case, and the number that I use as a multiplier is 1.24. So I take the horsepower, and here's an example. Example 750 times 1.24, and you'll be within a couple CFM of 930. So when somebody tells me how much power they're making, I can tell you how much air you're taking. All right? If somebody's got a big secret and they don't want me to know something, I just ask them one question or the other question. I work with a lot of Cup teams on plate motors. They tell me the power. I can tell you the air. I've never missed it more than 1 or 2 CFM. So we're going to go through this formula because it's a very helpful formula. Okay, you take CFM times 12 to get square inches. Back to the example again. We have 930 CFM times 12 gives us 11,160 square feet per minute. Now we got square feet per minute divided by 60 gets square feet per second. Example. 11,160 square feet per minute divided by 60 gives you 186 square feet per second. Second part. Square feet per second per cylinder, so we can find mean airspeed. Same as the example before, 186 feet per second. And then we're going to take, and up, excuse me, right here, I have a typo because when Bob was there before, so in your sheets, where it says ports per cylinder, this is ports per cycle. So if you would correct that. All right. So then we're looking for 186 feet per second times the ports per cycle, which gives you 744 feet per second. So that's mean airspeed divided by ideal port speed. Gives you the ideal port area. So 744 divided by 267, which I'll comment in a moment, will give you 2.785 square inches. All right. Now the comment is any given number, the 267 that I've been using for a long time, applicable everywhere? Absolutely no. If you have a plate engine up to a pro stock engine, you'll find that the mean airspeed does change. Because the more restricted the engine is on either end, whether it be a plate or a muffler, tends to make the air move more slowly. And many times the optimum combination will have a slightly different number. A pro stock number will be closer to 300, a plate motor may be closer to 240. So if you're developing this particular thing, the object is you find a combination that works for you, you begin to predict your future based on your atmospheric conditions. Once an engine size and a horsepower requirement are determined, then you can calculate port area, RPM range for piston speed, and stroke for piston position. As we said before, you could take the 930 CFM and you take the ideal VE for your engine application. That'll give you RPM range. You take RPM range for optimum piston speed for your type of fuel you're running, because it's based on burn rate of fuel. There's no absolute numbers. The thing that I'm trying to do is tell you the concept. If you have methanol or you have each fuel has a burn rate. But you can change and develop new engine combinations based on what you're most familiar with. Now I can begin to look at valve to bore distance and valve to piston distance. One of the things I was beginning to think like John 101. The engine only recognizes its own needs. Flow per crank angle designed around limitations or restrictions. Event timing takes precedence in maximum performance engines. Example, pro stock, because the engine still recognizes flow per crank angle. A pro stock engine is valve restricted. Event timing depends on air density and pressure. Peak velocities may increase or decrease with change in nose area, camshaft. When the head begins to improve, you can carry so much velocity into the cylinder that you begin to discharge it back, and they've named it many things, reversion. What we have found is if you, I'll continue with this in a moment, if you reduce the nose area, you'll carry less speed in cylinder. Okay. How do we know when we have too much or too little nose area? By how the engine carries from peak power to peak RPMs. What we're beginning to do now is to think in a system-wide approach. So we know when we get to the engine what we're going to have to recognize. Some people might not be aware. I didn't draw everything in AutoCAD for this. Some of them got quick because July 28th I was hit by a car, so I was busy recouping. This was a hand sketch. Port taper. Once area is acquired, determining where the taper begins depends on range and performance needs. If you're looking at, for instance, a dirt circle, which has tight turns, we usually run a constant area from the bowl to the plenum. I just drew a line here for this is where the cylinder head separation would normally be. But if you go to the other extreme, pro stock, which is a valve-restricted engine, that taper will begin right at the valve seat. All right, and continue up through the head and up through the plenum. Now we start to get to some of the drawings. Computer-aided design. AutoCAD helps with corner radiuses and tapers for proper area. If there was time, I would have showed how to make the runner hand forging dies with the corner radiuses. What this allows me to do here is to show you that the area is calculated for both the cylinder head surface and the plenum, and the taper is calculated. So what we're doing now is developing the process of thought, from writing the first note to realizing that we're going to have a form of racing that we're going to complement and where we're going to begin the taper. In the single 4-barrel applications that I do, I run constant area through the head, and I begin the taper at the mating surface for the engines that I do. Pro stock, then I would begin them at the valve seat area. Port choices are based on when valve curtain area exceeds critical area, when the arc used has enough area to support the flow, or when sufficient flow path is available to the mixture so that the valve is changed from an obstruction to a flow aid, aiding in the direction. Conventional ports is when, either by rules or engine limits, the valve area is restricted and it is in the flow path 360 degrees of valve. Well, one of the things I wanted to begin to do, and I wanted to, is thinking like a droplet. When I was first doing a lot of porting, I used to think like air. And I realized at some point that you really do have the fuel. So you got physical limits and port location over bore, which determines droplet path. Yes, this is a lot of thinking. I wrote that on my own note here, because when you're looking at these examples, and I drew them in hand because I was trying to make them representative. A lot of times, depending on where the port enters the bore, right, you can have a different pathway, a drop pathway. All right, and I did this simply at the time, and I thought it was a really good effort. I took a piece of tape to begin to let you know, giving a droplet a headache. The forget and flow component, the piston, can help or hurt droplet motion. Short strokes like directional ports. And when I put that tape in that same drawing and took the photograph again, one could begin to see that in some cases we could have a head that flowed very well on the flow bench, but once it got onto the engine, it didn't respond as well because the droplet path now became a problem right here. So that's why before we start doing anything, we start thinking. The next photograph, we simply move the tape down, removing the headache. Long strokes like conventional ports. Because now you can take the same thing here, and if we go back to the last slide again, you'll see that that port that was now running into the piston, because it would have been a short stroke, is now an enhanced design for the droplet. Making the droplet comfortable. Port orientation can help or hurt droplet path. Well, down on the bottom here, hopefully it comes out on your thing better, is when you're looking at the orientation from the vertical appearance. You can have a Ford port would be this one in here is demonstrated in the black, or they had a Dart Buick would be this one in here in the red, and then you go down to a conventional Chevy, and then you go over to what they would call short port style Pro Stock port, all giving the droplet orientation. This is before we've done anything. We're beginning to get these concepts. When I'm out jogging, biking, or hiking, I'm realizing what my ultimate goal is. Not confusing the droplet. Directional port molds help also check area. Droplets hate area changes. So when we've done these things, what we also do after we get just our basic ideas started, we begin to know that we don't want the area to change. And before I started running molds, I didn't realize that you could make a port flow pretty good, and you take it out and it looked horrible. I mean, enough so that it would visually know that it wouldn't work. One of the, both the long and short turn areas tend to be something you really need to measure in a mold situation. This is my favorite, Wowie Pro Stock conventional port. Bore-supported droplets. And this is a little hard to see, but this is actually out of a fairly competitive Pro Stock. And if you can see it from the, if I can go back one, the directional port, all right, a directional port is configured completely different. And that's just what I wanted you to see. A competitive directional port versus a conventional, a competitive pro stock port, where you're using 360 degrees